retaliation like. Watch your eardrums pop, pop, pop. Watch your eardrums pop, pop.
We are about to embark on a journey through the ear. Our magic wand will help guide us. This is the pinna, aka the auricle. Because of its shape, it acts as a funnel, gathering sounds from the environment and channeling them toward the ear canal. It also acts to resonate high-frequency sounds as they are funneled into the external auditory canal. It amplifies these sounds to ensure they are heard and processed by the inner ear structures. It also helps with directionality and localizing sounds. One ear might catch a sound faster than the other, so the person will know where the sound is coming from and where they are in space. My magic wand is now guiding us through the external auditory canal. It's not the internal, it's external. Here is where the air warms up so that when it reaches the eardrum or tympanic membrane, it can function properly and to its full extent. The external auditory canal is a tube formed on the side of the head, beginning at the concha and extending inward at a slight upward angle. Its outer or lateral third is cartilage, and the inner 2/3 are osseous or bony. The lateral cartilage portion is where the production of cerumen or earwax occurs. Cerumen is associated with a negative connotation, but it's good. It protects the external auditory canal and the tympanic membrane so that foreign objects or bugs do not enter, and it also naturally cleans it out, so there is no need for Q-tips. Next on our exciting trip is the tympanic membrane, aka the eardrum. Can I get a drum roll, please? Oh, okay. I will be taking it out of the ear model for clarity. It is a concave, disc-like structure, and it marks the border between the outer and the middle ear. It aids in improving sound transmission to the inner ear. The tympanic membrane vibrates when struck by sound waves. It also assists in the impedance matching system. Now let us present to you the ossicles! We have now entered the middle ear. The middle ear changes acoustic energy to mechanical energy. This is the malleus. It is the largest bone of the ossicles. It aids in the impedance matching system and articulates with the incus. When the malleus articulates with the tympanic membrane, it forms the umbo. The umbo and tympanic membrane act as a lever to help the middle ear's impedance matching system. We have the stapes articulates with the incus. I'm going to be taking it out so you guys can get a better view. The stapes foot plate occupies space on the oval window by the annular ligaments. The impedance matching system of the middle ear occurs by the ratio of diameter of the tympanic membrane to the oval window. The size difference causes a significant increase of pressure. It's about 17:1. This causes a 30 dB increase. dB equals decibels. Also, the tympanic membrane and the umbo and the ossicles move in a lever action to assist in the impedance matching system as well. The ossicles do not move in a straight line from the tympanic membrane to the oval window. Rather, it rises into the attic of the middle ear and falls again over the incus, providing an increase of force at the stapes.
the eustachian tube. It equalizes middle ear air pressure to ambient air pressure to maximize the tympanic membrane's mobility. It also removes the debris and mucus of the middle ear. Last, but certainly not least, we visit the inner ear. Now we're going back to the stapes. As we mentioned before, the footplate articulates at the oval window. The inward and outward motion of the stapes on the oval window causes the fluid in the cochlea to move. This fluid moves in the scala vestibuli, which is seen here by the red. The scala vestibuli is the tunnel of the cochlea that articulates with the vestibule of the cochlea. When the stapes pulsates on the oval window, the fluid, called perilymph, displaces the scala vestibuli, which causes the Reisner's membrane, seen right here, to shift. Here seen in the white is the scala media, which is an endolymph-filled cavity located between the scala vestibuli in the red and the scala tympani in the blue. It houses the sensory organ for hearing. The scala tympani also contains perilymph, just like the scala vestibuli, and it articulates with the round window of the middle ear, seen here. It communicates with the scala vestibuli in the red at the heliocentrema, which is at the very top. When perilymph of the scala tympani pushes against the round window, the oval window is in opposite position.
Here is a picture of the organ of Corti inside the scala media. As said before, when the perilymph is displaced in the scala vestibuli, the Reisner's membrane shifts. This causes the endolymph in the scala media to shift as well, which then moves the basilar membrane. This causes the hair cells to shear and the cilia to bend. When the hair cells are stimulated, it improves the frequency, specificity of the cochlea. The conversion of mechanical energy into chemical, mechanical, cochlear energy turns it into something that the brain can understand. Each neuron is stimulated by its hair cell, and this information of the frequencies are sent to the auditory nerve.
The modiolus is at the core of the cochlea, and it stems into the cochlear nerve, seen here. The cochlear nerve combines with the vestibular nerve, forming the vestibulocochlear nerve in the internal auditory meatus. The internal auditory meatus houses the vestibulocochlear nerve, which is the 8th cranial nerve, and the facial nerve, which is the 7th cranial nerve, and allows them to enter the brain from the inner ear. This is the vestibular system. It is a reflex system that works constantly to send signals to our brain, which in turn signals our ocular motor system and informs it on which way to go. These are the semicircular canals. They're membranous labyrinths. This is the superior semicircular canal, the posterior semicircular canal, and the horizontal semicircular canal. They are used to detect angular acceleration of the head. The utricle, seen here, and the saccule, seen here, are used to detect linear acceleration. The utricle detects horizontal acceleration, like walking, and the saccule detects vertical acceleration, like jumping. The semicircular canals, seen here and here, as well as the utricle and the saccule, are filled with endolymph and surrounded by perilymph. Our vestibular system tells our eyes where we need to be looking, and as well as telling us where we are in space.
This has been a great journey, and I hope you've enjoyed the ride.